Good evening. Today we will study a theorem that is usually called the Fubini's theorem. It is about the iterated integrals of scalar fields. So this is a scalar field is a function that is defined on a vector space. So with that in mind, we have here the theorem. It tells you that if we have two compact blocks, so this is just for we will study just a function that are defined on a compact block itself that we can separate as two parts. So we have one block, one m block and one n block that make up that m plus n block. So if we separate the domain in those two blocks and we fix an arbitrary point in the first block, we can define a function that is denoted as f sub x, which is that's the function defined that, but it basically means that you let y vary over its whole range, which is v sub 2. And then we fix that x there. So f of x evaluated in y is equal to f of x in y and y. So that's kind of easy to understand. Then from this function we define two functions. So the first function, which goes with an L that stands for lower, is defined on the first block in which we fixed our x previously. So now we will make x vary, and that L of x will be equal to the lower Riemann integral of f of x evaluated in y, but over this domain. And on the other hand, you have that u function. U stands for upper, that is also defined on that block, and here we have the upper Riemann integral. So you know, since f is it's a function that is Riemann integrable over that block, that big block, then automatically f is a bounded function. So as bounded functions always have that lower and upper integral defined. So these are numbers. And you know, the fact that f is Riemann integrable doesn't mean that this function f of x is automatically Riemann integrable. It doesn't hold. What we do have is that the points in the domain in this domain V2, in which f of x is not Riemann integrable, are literal, and literal in the sense that the set of not discontinuity, but the set in which it is not Riemann integrable, it has Lebesgue measure 0. So that's part of Fubini's theorem that we will not cover today. We will just prove that given this previous definition, we have that those L and U functions are in fact Riemann integrable over V1. And it also holds this equality. That doesn't mean at all that L is equal to U. It is not saying that, but that the integral of L and the integral of U are equal, which is entirely different. And then they are not only equal, but these whole integrals are equal to the integral of f on its complete domain. So this is the theorem of iterated integrals, as I told you. And now we will prove this result. So let's get into it. First, let's work on the partitions of v1 and the partitions of v2. So let's call the piece 1 that will be the partition that is composed of these subblocks, and this is a partition of the block 1. So we also define a partition of v2 that we denote like that. So these are partitions, and then from these two we can define yet another partition that is this product that we define just like that. So this is the domain of F. So we have that, and we can then define the lower and upper sum of F in P as defined here. So this was for any two partitions of v1 and v2. So this we go by definition here. So this will be the lower sum is with the volume of, like that, right? And we can decompose these as the product of these two volumes. This is clear. And then we this is a sum that ranges from those two indexes. So this is a finite sum, right? And but we can separate this sum in as a successive sum. We start first with this index and then with that other index, and then we just copy everything else. This was like that, of F in those volumes. Like that. So then since we are first making j vary while I is a constant, so this will be a constant which we can take outside. So this will be and then we take outside that constant, which now is varying here. All right, so now we wish to analyze what's happening here. So let's say that we have some point x inside of this subblock. So then it will follow that this is the, well, we can say that here, well, not x, oh yeah, x, such that x I think it is clear like that. So this as an infimum will be smaller or equal than this other infimum. So this is for arbitrary, or perhaps we can let's put a hat here. And why is that? Well, because you know, this is equal to, only put it here, this is equal to x hat and y. So this is in fact this is a subset of this. So as we know, when you take the infimum of a subset, the infimum is bigger or equal than the previous infimum, just because it is a subset of that. So this will hold, and this is equal to m of j of f of x hat. So well, I think I forgot to. This was in 1 and 2. Yeah, this wasn't entirely clear. Because we have the indexes here. So the indices should be the same here. So now it's clear, and that's why we this also should be corrected accordingly. So we carry that index here because it is the infimum of the function that ranges over this subblock. All right, so we have we are proving then that is smaller or equal than for every x inside. So we have this here. Then it will hold that we will have that. Let me add a page, or yeah, here. When we have these so this, let's analyze this part here. So let me copy it and put it here. So we have this, that this is small than this holds here, but then this is in fact the lower sum. This is the lower sum of x and by the partition P2, because P2 was defined as this partition here, and since we are making J range over its whole index set, then this will hold. So this is you know, for that x fixed, for that fixed x that I don't think we fixed it previously. We can, well, we choose one of those. It could be say that well, it's in fact for every. So if we fix one of those, we will have that, and yeah, this will hold. Alright, so this will happen for any of those, and by definition, if you remember, the lower Riemann integral was the supremum of those lower sums. So this thing here is more or equal than, since it is a supremum, than any of those lower sums. So we have that, and this is the definition of this function as we stated here. This L is defined like that. So we have proven that. Let me use another color. So we have this proven, and so we can replace that here. Probably we can replace that. So since this is, as we are seeing, is greater than L of x, we're seeing that here, and this is for any x here, then this number is in fact a lower bound of this set here. So if it is a lower bound, then this will be naturally more equal than the infimum of that set, and the infimum of that set is none other than this element, this number. So that is, I think that's clear. No, I write it like that. It should be like that. So now it was looking weird. So as the infimum if is the biggest lower bound, then this is a lower bound, then this number will be more or equal than any lower bound. So we can write that here. So we have that this times the volume of is smaller than times the volume of, like that, right? But this here is the lower sum of L in the partition 1, and this is because the partition 1, as we defined, was the partition that had those subblocks, and here we're making those blocks range over its whole index set. So this is the lower sum, and then we are this was equal to the lower sum of f in P. So we have proven that this holds. and let me add the page here. So we have proven that this holds. Let me highlight it. Just like that. Similarly, we need to prove a property regarding the upper sum and the upper sum of the other function. So with a wild guess, we can say that this happened, but let's put this on hold for a moment and make the proper analysis here. But the analysis will be totally analogous to that previous one. So perhaps we can just make the adjustments here just to not write everything all over again. So let me use the pink color to make the changes. So here, instead of the lower, we will go with the upper. This will be capital letter M. This also be capital letter M. Similarly here, capital letter M. And so yeah, now we fix some here, a capital letter M, and this is the supremum of this. And since this is a subset of the supremum, it decreases a little, and that will be this here. So this is summarized like that. So that means that this is heavier than this, which is equal to that upper sum, and then since the upper integral is the infimum of those upper sums, then this will be like that. And this is the definition of the u of x for every x. And then we will have that this is heavier than u of x. And then we came back here and this was bigger than u of x. So this is an upper bound of u of x. So that makes the supremum, it was the smallest upper bound. So the supremum will be less or equal than that upper bound, and the supremum was this notation here, like that. So you have that, and then that will make this, which is the upper sum, bigger than the supremum here, which is the upper sum of this here. So that will go like that. And yeah, so it's the same analysis but making the proper changes. So it was a fairly quick. Now we highlight this here. So now we will use these two properties. We need to write them here, starting from the left side. We have this from this, but this is smaller than, because you know, any lower sum is less or equal than its upper sum, because, well, because we are in the same function L, right? And then this upper sum here shall be less or equal than this. And this is, let me highlight it here. This is because the way it is defined. Why is that? Well, because this term is always smaller or equal than that. Just by the way they are defined, you have this happening. So if this happens, then what about the upper sum of those functions? Then the upper sum is the supremum of here. So the supremum is the smallest upper bound. So this is well, just this is a property of real analysis. So from here it holds that so because this is a property that we can quickly state here in its most general form, if for every A in A exists V in V, such that this is a property of real analysis, of the first course of real analysis. So yeah, this will mean that this happens. But then if this happens, then I'm doing the complete proof here in this little space, times the volume of will be smaller than this here, but that on the left side is none other than the upper sum, and the other is the upper sum of that function. So that explains this step here. Everything is well it is on good ground, so we are not making anything to chance here. But then we have that this is smaller or equal than that. So we write this here, just like that. So from here we have that, you know, we were told at the beginning that f was a Riemann integrable. So if this holds, then if f is Riemann integrable, then we can shrink I mean, we can't you know, make the oscillations go as small as possible. So we go with this other characterization of Riemann integrals. So f is such that so this is here. So since this difference is smaller than that, then clearly this with this will also be smaller, right? So that makes this makes L a Riemann integral over this. So this proof that this function is Riemann integrable. So we need to make the same analysis for the other function, the function u. But we already have the means to do that here. We don't need to make any extra analysis. You just need to keep in mind that it is, while this is true, it is also true that the infimum of A will be this also holds. It's like if you have with blue, let's write the elements of A, and with orange the elements of V. Just to get an idea. Then the infimum will be around here, and the infimum of B should be around here. If this is not a case, if the infimum of V could be like from here, then we could make some small neighborhoods that is strictly less than the infimum of A. And well, for yeah, if we make that neighborhood, it will be an element of B here, which doesn't help at all. Well, yeah, if it was right. Because in our specific case, perhaps not in the general sense. So I really have doubts about this. I think this is wrong. But for our specific case, it is true, because this will be some u of x. But then we are saying that L of x is always smaller. But then this will mean that L of x is really less than the infimum of all of the L of x. So this is a contradiction. So it's necessary that this happens. So yeah, not in the general case, but for our case. So let's make a line here. Please don't get confused here like I did. In general, this property does hold, but this other property not necessarily. But for our special case, it does hold. So from here we replace this with here, and then we will have that this happens. So the lower of L is less or equal than the lower of U. So how does this relation help us? Well, we have the lower of L here, so this is smaller than the lower of U. But again, the lower of U is always smaller than the upper of U by definition of lower and upper. Then this will also with blue, let me write it with blue. This will also constrict and make small the oscillation of u as desired, like before, so that will make u a Riemann integrable function. So yeah, it took a little of thought there, but now we have that both functions are Riemann integrable, which is already half of the proof. We are here, we are good. And now we will prove that last part of the proof. So this is the iterated integrals. All right, so let's do this. So we want to prove that the integral of L of x is equal to this other integral, and this is equal to like that. So let's start by this is to prove. So let's start by defining these two sets. So first we will define a set of lower sums. Let's say A is a set of lower sums of f, in fact, for every partition here. And then we define a set V also of lower sums, but of this other like that. So we had here that every lower sum of f, it was smaller than the lower sum of L. Well, given that P is equal to P1 times P2. But at any rate, this is still under this part. So we will have that the supremum of A is less or equal than the supremum of V. This is a fact. So do not get confused with the one below that I wrongly thought it was right in the general case, but was only right for our case. So that means that the supremum of A is smaller than the supremum of V, but the supremum of A is, well, you know, it's this here, and the supremum of V is this other here. But it happens that since L is Riemann integrable and F is also Riemann integrable, we can forget about those symbols because they are equal. And from here we have that. Well, we want to do the same for the infimum, but once again this won't work at least directly. So we kind of want to get something like this, I think. Well, not with V, so let's do B prime. Well, I think I got it. Let's do it here. Let me highlight this here. Yeah, we another color. So let's put this into the box for a moment, and let's think about our A prime, which is the set of upper I think this could be a more simpler than I thought it could be. So since we had this here, so upper of here we have exactly the we have that for any yeah, the upper of u is smaller than the upper of f. So the upper of u is this. Oh yeah, whatever. There exists v in a prime such that a is smaller than b. So yeah, we have that. I think it's yeah, that's okay. So we want to show that the infimum of v prime is smaller than the infimum of a prime. I think this is because the infimum of v prime is equal to the upper integral of u, and the infimum of a prime is the upper integral of v, like that. So we want to show that. So this is because, and u is a Riemann integrable, so that can delay that part. So the thing will be to prove this fact here. So yeah, let's go with a graph to see if it's actually right. I think it is, but let's do a graph here, a little graph. So with blue, let's put the elements of v prime, and with red the elements of a prime. So we want to prove that the infimum of v prime is smaller than the infimum of a prime, which once again, since this is let's go with the reduction to the absurd. So let's look for a contradiction. So what will happen if the infimum of a prime was strictly smaller than the infimum of v prime? Well, then this will be here strictly smaller. Then around here we will have some element of a prime, which is this one. But then you know, we have that here. So this is bigger than, so there you have it. So given that p is equal to p1 times p2, so we can always make that, and then we will have that well, some element of b prime is strictly smaller than its infimum, which is a contradiction. So yeah, it is right. This is right for our case. This is right for our case, because I think in the most general case it wouldn't be true, because we're saying that perhaps it could be true. Yeah, it is not true in the general case, because having some more elements here wouldn't go against this, because we are not saying that every element of of A prime is bigger than some element of A. So this in the general case is not true, not true in general. But in our case in particular, it is. Because we have a bigger condition than this existence. We have a, this is a stronger condition. So with that in mind, we have this here. Let me highlight it with yellow. We have this here. Together with what we proved above, we have that, and this is the end, I think. Because of this here, so we have this thing here, but you know, it also happens that this implies by properties of integrals that so this is smaller than, and this is smaller than that. So this makes, let me add a page here. This makes equal to, and this other makes this equal to that, and so that shall be the end. I think I explained with detail every step in the proof, so everything was well explained, I think, even though we took quite a bit of time. I think we got everything clear up and everything nice explained. All right, so this is the end of the video. If you found this video interesting, please consider giving a thumbs up and subscribing. I will talking next about, well, we continue the next step of your course of real analysis will be probably starting to make the ground to construct the abstract integration, the Lebesgue integral. So if that is the case, then please go into my channel and review the videos that I have about the introduction to measure theory, and then you can start to study abstract integration, because abstract integration comes from measure theory. So yeah, the next step will be to study measure theory. This is probably the end of our basic real analysis lessons. But you can still hang around the channel with the other courses and stuff. So see you around.